telescope is warm, at warmer temperature, you would just see the glow from the telescope. So to operate in the mid-infrared, you need to operate at this temperature, minus 40 Kelvin. So to get there, you can do different things. You can either actively cool the telescope, which is a very complicated system to keep the temperature low, or you can passively cool. Passively cool means that you put a sunshield. And the sunshield orients itself so that the telescope is always facing the opposite side of the sun. I'll show you that in a minute. Under here is the instrument module that you see here in the clean room. So, a huge international collaboration. I think this is very important to stress that if you go, we had just a workshop last week, a forum on international cooperation, and we all love this thing. If you want to go fast, you go alone, but if you want to go farther, you go together. And the reason is that if you want to build something ambitious, you have to put different agencies together. So in this case, this is a collaboration between NASA, ESA, and the Canadian Space Agency. 14 countries, including Switzerland, were really involved in this mission. So at the level of coordination, you know, international collaboration is a plus. It also adds overheads in terms of communication and everything. Things take a little longer, but at the end, it's really worth it. 27 years of work. The work started in 1995. So this is the sort of lead time that a mission of this magnitude takes. So it launched, finally, on Christmas Day. This was a great Christmas present for all of us who had been suffering through the delay. It went from Kourou, the European spaceport, on an Ariane 5. This was when Ariane 5 was almost put up, you know, was at the end of the lifetime, but Webb had to go, has been designed exactly to fit, as my little mock-up there says, in an Ariane 5. It was actually fascinating to listen to the countdown in French. It was refreshing, so there was an interesting added touch. And it was a great success. And because the launch itself was a great success, we had the orbit insertion. It was perfect. So how does the telescope maneuver? There is fuel on board. There is a limited amount of fuel. And so at the beginning, if you have to use the fuel to correct for the orbit, you already cut your lifetime down. But this didn't happen because it was so impressive. And so I can say now that we're looking at 20 to maybe 30 years of lifetime from the original 5 to 10. So a big success. This mission will be with us for a long time. So I want to show you here, this is actually the final stage. This is the telescope that is moving away from the rocket, from the final stage. And I was part of the conversation at ESA on whether we wanted this camera on the rocket or not. I mean, it's expensive to put a camera on a rocket. And so everybody, you know, at ESA we were saying, well, do we really need it? Well, it was so fantastic, and these images, you've probably seen them in the newspaper, that at the end, ESA decided they were going to put cameras on all the rockets, exactly, to capture this kind of imagery, so little nugget of. So where is JWST? It's at the Lagrangian point 2, which is a potential well, quite away. It is sort of a million miles away from the Earth, well beyond the Moon. It takes a month from here to there, and it's not that JWST is in one point specifically. It kind of orbits around, because there are other missions at L2. There is Herschel, there are, and others. Oops. No, we don't want to do better configuration. And as you can see that in all these motions around the sun, notice that the sun shield is always facing the sun, and the telescope is protected. And this is exactly to allow operations at the temperature that we need. So on the way from launch to L2, it took a month. During the month, the telescope unfolded. And so what you see here are the steps of this unfolding. Of course, we didn't have cameras on the telescope, so what you see here is the simulation that was appearing loud, in a giant screen inside the control room, because the engineers were following step-by-step the telemetry to make sure that all the deployments happen, that all the release mechanism went, all the pulleys opened, that the 155 motors actually kicked in when they were supposed to. As you can see here, for example, is the deployment of the sunshield. First you have the side booms, first one, and then the other, and then you have the opening of the 5 layers. All this thing was done in the clean room over and over again, and I can tell you at the beginning there were problems. There were, the first time that they did the opening, they ended up with some sort of interesting shears in the captain. And then slowly, things were fixed and repeated. And at the end, the final, and you see the number of days that it took to get to that deployment. The final deployment was the mirror, when, with the mirror, the petals of the mirror opening up. So it was flawless. And this is a testament that when you put, excellent engineers and scientists working together on a project, you really have success. And success was the first image. And so I was in the room when that image appeared on the screen, and I can tell you that there was a moment, of course there is the first celebration, the wow, that star was supposed to be a single star in a dark, empty field. Why it's important to take a single star? Because we wanted to check exactly what you see, that fancy diffraction pattern, which is basically created by the mount of the secondary mirror. So to see if everything is aligned, that image had to be perfectly symmetrical, and all the things that you see, you go, oh my God, what are those? They were expected, and people were very happy to see them. But then we saw something else. We saw stuff around it. And the stuff around it, we couldn't understand. We thought, oh my God, we have contamination in the detector, something happened. Then people looked close by, and there were galaxies. Because we quickly realized that there is no dark spot with Webb. The system is so sensitive that wherever you look, you see all the way through the edge of the universe. So that was the first, and immediately one image of a very distant field was taken. All you see here are galaxies, distant galaxies, and interestingly enough, you see these arcs. These are basically created by a phenomenon called gravitational lensing, when you have a cluster, a very massive cluster of galaxies in between us and the object that you're looking. The light of that object is deformed and creates these arcs. And why are they useful? Because in the arcs you can actually see it's a distorted image. Look at this one, for example. It's a distorted image of the galaxy back there. So you can get information. It's just like we call it nature magnifier mirror. You can see things that you would not be able to see otherwise, because they're much farther away than what your object is. So this image was so spectacular that basically circulated quickly around. Now, I want to say 2 words about the first images that were released. I was part of the group that actually selected the target for those images. And we worked, this seems, you see the image and you go, wow, and you think they magically appeared. No, a group of people actually worked for a couple of years. First thinking what targets would look good with this new telescope. We didn't know the performance of the telescope. So for example, one of our driving criteria was, let's not use anything the Hubble has looked at, because we have this iconic, machine that produces super pretty pictures. And what if the Webb pictures are not as nice? What if they look bad in comparison? So we said we have to look at new things. So we took inspiration from other infrared missions like Spitzer and Herschel. We went and looked what they had done, and we tried to find photogenic targets that we could use for this. And this list was kept super secret for a long time because NASA and ESA as well, the Canadians were, okay, whatever. But NASA and ESA were really, really worried that it would have been leaked to the newspaper, that the VLT would have looked at it and published a better picture just before the big splash. So it was a fascinating time. But this is just to say that at the end, when the images appeared, and this was one of them, we were really blown away because it was exactly what. So what you see here was an image that was taken almost, the telescope and not, the instruments had not been calibrated. It is pretty much as raw as it can get. And already, it's pretty spectacular. It was so spectacular that made the cover of Time. It was everywhere. Of course, we had other images as well. And I'll come back to this. This was an image that already had been taken by Hubble in a different location, but then we went back and looked at it with the Hubble just to check. If you have a question about the colors, hold that question and ask me at the end, because that's an entirely different conversation, and a lot of people have spent a lot of time thinking, and it deserves an explanation by itself. But Stefan Quintet was another one of the, this is 5 galaxies, a couple of, it's an optical alignment plus a group that are actually interacting, and Webb immediately, saw the young star formation, the young cluster formation happening, so immediately it was, it's totally beautiful. So first celebration, of course, everywhere. I think we were very proud to say that we share Times Square with the latest musical happening at the time. The Empire State Building, was gold for one evening. I don't have a picture, but the Eiffel Tower was also gold for one evening. And what you see here is a little snippet. I mean, this image went all the way to the President of the United States, who loved it, invited the scientist, Jane Rigby, who is now the senior project scientist of Webb, was invited to the White House, and you can see the President. So anyway, big celebration because everybody went, phew, it works, and it works really so well. We had an event here at ISSI. Maybe some of you were part of that event, but this is exactly the moment when ESA showed their, targets, which are part of the same sample. So we had, we had fun here because we had organized a sort of all over the world kind. This is a mission that belongs to everybody. So we had an all over the world kind of celebration, and so this was fun. So let's start looking at what kind of science, finally, we can talk about what kind of science Webb has been doing. So, and at this point, after seeing the first image, we're not shy anymore to see a comparison between Hubble and Webb. So this is M16, Pillars of Creation, iconic Hubble image, was first taken in 1995, and then was again revisited later on. You can see here, this is in the optical with Wi-Fi camera 3, actually in the I band. So what do you see? You see a lot of dust, this pillar, but these pillars are shaped. they're shaped by what? They're shaped by very massive stars. Very massive stars have this characteristic that they have very powerful winds. And the winds kind of sweep the material that is around them. So there were very massive stars behind, and they had rolled and shaped these pillars. Of course, astronomers were interested to know, well, I get it, but there is nothing else. What are the young stars? What are the small stars? For that, you need to go in the infrared. And when you go in the near infrared, so this is NIRCam, we basically looked in the near infrared, you can start seeing through these pillars. And you see actually all the stars. You see many more stars. And then you can really start doing the census of that stellar population there. And then you go, well, what if I look at it in the mid-infrared? And this is what you see. Now the stars are no more, because the stars are very faint in this wavelength. But what you see, you really see the dust. And so you can really do, and dust is the fundamental fuel to make new stars. You need the dust and the gas to make new stars. And so here you basically can really do the balance of the mass and the, how you make stars. This is one of the fundamental questions that astronomers have. But you cannot do it if you look at the optical, at the visible part alone. You need the full color length. And just to give you an idea, so this is the size is 2 light years. So there are regions that are kind of nearby. We're not talking about distant stuff. So, as we said, one of the scientific targets for Webb was to look at stars forming stars. This is a sort of mystery. We still don't really know. We kind of know that you have a molecular cloud, starts collapsing, the gravity allows the cloud to collapse and then starts to contract, and then when you get a certain density, you start creating reactions that start warming up the star. You have first a protostar. Usually protostars are recognized because you have these powerful jets. You also see here, they accrete mass from the cloud. They kind of shape it, but then in this case, for example, you see that there is a jet here, but there have been subsequent episodes in this jet. And you see the material coming out from the star hitting the material that came out before. And so you have these very interesting shapes. But this is what astronomers really needed to understand, how these objects, formed and how it will become a star, a full-fledged star as we know them. Objects at this kind of age, which is a few thousand years, we call them big arrow objects. And we see them in the visible, we see them from the ground. Again, Webb with a 6.5 meter mirror can see details with a clarity that was never there before. And then you start seeing things like, look, this is there is almost a torque mechanism in this. That means that the jet is sort of rotating. And why is rotating? Because probably here there is a star that is double. So you have a rotation and you have a jet coming out, and you see this sort of corkscrew effect. So these are things that we didn't see before. They are completely new. And with this resolution, you can really make quantitative studies. Here is another one where you have this sort of corkscrew effect. This one is big arrow 46 and 47 because we actually know that there are two stars. And here in the center, you can see that the central star is elongated. So all this now is in the archive, and people are using this data and just having a field day analyzing the data and very busy writing papers on what they see. Let's look at the Carina Nebula that we talked, I showed you at the beginning, was one of the early images. So you see here, this is Hubble, this is Webb. Same lookup table. I'll talk about the colors after. But you see the difference? This is near come. Sorry, this is visible and this is near come. Same effect. We see these clouds that are shaped by very massive lunar star behind, but here we see all the young stars embedded that are actually forming out of this reservoir of fuel. So this will really tell us how stars, finally, how stars are forming. And of course, this I'm showing you pretty images. You don't believe, you know, astronomers love to show pretty images, but what the science is done with spectra. The science is done by decomposing the light in its component and see the chemical and physical properties of the elements that are there. And this is really interesting. This, for example, the quality, I don't want to go in much detail about what this means in terms of chemical elements, but what I want to show you is the quality of this spectra. So NIRSPEC is the instrument that has been provided by the European Space Agency. And this is the workhorse. 60% of the time on Webb is used by NIRSPEC. And you know, when you look at the signal to noise, that means how not noisy are these curves. This is basically just like incredible for people to see, because suddenly you can do really quantitative work with this data that was not possible before. So this is one close to my heart, NGC 346. So I study stellar clusters. Why do I study young, massive stellar clusters? Because you know, we catch them in the first 3 million years. This object is like 3-4 million years. This is in the Small Magellanic Cloud. It's big. It's really big. Just to give you an idea as to how, back. Sorry. It's approximately 200 parsecs across. When we saw the first Hubble image, we realized we started here, because of Hubble Small Telescope, you can count the individual stars. You can measure the photometry of how bright they are. You can put them on diagrams that tell you exactly what their temperature is. You can compare colors, the temperature, and you can figure out what you're seeing. And what we saw here is that there were like 17 clusters, subclusters, including these 3 at the center, which we could tell with kind of certainty that they had formed together at the same time. They were coeval. This thing went whoop and formed all these subclusters at the same time. Over this scale, which is huge. So then what's the next question here? Then you have to figure out there is still dust, there is still gas. Don't worry about this concentration. This is a globular cluster, which is just a random coincidence. But JWST is telling me how much fuel there is still left to form new stars. And are there stars that are forming out there? So this was one of the first images that was taken by NIRCam. And it was kind of, people are now writing the paper about it. So let's look for a minute at the late stage of stars. So we're now looking at stars that have spent their life, they formed, they lived as full-fledged stars, and then what happens at the end. Some of you remember supernova 1997A, a classical example of a beautiful supernova that was caught in the act of exploding, bipolar symmetry. Then, inspected and observed for many, many years, showed these beautiful pearl necklaces astronomers were. It's basically the radiation that hits layers that have been expelled before. But over time, interesting, we see that the central object, which had completely been disruptive, like supernovas typically do when they explode, it was becoming a supernova remnant. And therefore, when Webb looked at it, we were really impressed to see that now it's not a star anymore. There is nothing left from that explosion. The pearl necklace is still there, but we can see now where the dust is because it's cooling down. And so this is complementary to Hubble, and this will become a proper supernova remnant that astronomers will classify as such. But this was pretty impressive to see. The Ring Nebula is another example of late phases. There is a star here in the center that has shed all the outer layers. You go and look at it in the visible and in the or in the near infrared, and you have a complete different picture from the mid-infrared, which is to the right. And this is because you're sampling different physical properties. So here, for example, we see the inner ring with incredible details because this is the warmer material. Within the mid-infrared, you see the cold outer material. And so by combining the two together, or by studying the two together, you really get the full picture of how this ejection worked. This is another example. My student did a thesis on, this is a Wolf-Rayet star, Wolf-Rayet 124. Wolf-Rayets are very massive stars. They're above 8 times the mass of our sun, but they can be 20, 30, 40 solar masses. They eject a lot of matter in the space when they leave the main sequence, when they finish their life. This is an example of how one of these looked. We knew it can be even seen from the ground, but here you see the difference between the NIRCam plus MIRI, so near infrared, and then here only mid-infrared, where you just see the dust, the distribution. So by comparing these two images and to the optical, you really understand also how, what kind of material is expelled in these expulsions. So I think this was one of the first images that we took. Jupiter, just going quite fast because I have a few more things to show you. So Jupiter, this was fascinating. What can James Webb do on Jupiter? We know Jupiter inside out. We sent, probes on, next to Jupiter. So what you see here, whatever you see white means that is higher than the cloud on Jupiter. So the result here that is interesting is the discovery of a very fast equatorial jet. Very fast means Hurricane 5 kind of strength wind. We're talking of 350 miles per hour, 500 kilometers per hour. And, this planet has such a fast rotation of 10, hours that people could actually take images one after the other, and they started seeing this small feature which were effect of shear in the jet. And they managed to characterize the jet, the velocity, and also show how, turbulent. And we know that Jupiter is gaseous and very turbulent. We know that the white spot that you see the red spot that here is white. Why is white? Because it's actually higher than the rest of the cloud. This is a kind of vortex that is on the... So everywhere you look, you see things that you have not seen before. I want to spend a minute talking about exoplanets, because this is important work that Webb is doing using a technique that is called transiting spectroscopy. So transiting means that a little planet, basically passes in front of the star. Because the system is so stable and so accurate, you can basically see the dip in the light of the star when the planet moves in front of the disk. But how astronomers can use this in a very creative way, and actually, and Hubble actually has pioneered this technique, that you can go and look when the planet is around here, when it's slowly passing in front, and for a tiny period of time, you can actually see only the atmosphere of the planet, if the planet has an atmosphere. And you can do spectroscopy of that atmosphere. And we have seen that Hubble has done quite a lot of work on this, and Webb is just taking it to the next level. Because, again, think about it, you're doing spectroscopy of a little sliver of very faint atmosphere, and you can get a spectrum like this, with this quality that allows you to see features that are, they were never seen before with such a clarity. And here I want to there are a couple of examples, but for example, this detection of carbon dioxide in WSP-39b, you cannot argue about this, this detection. The dots are the data point. This has been taken during a transit. The blue line is sort of the interpolation, but this is solid quantitative work that is happening right now, which is moving the field forward. And, to the joy of theoreticians who are working in this field, suddenly we can provide them with high quality data that, yes, there are detections of fundamental molecules like water, carbon monoxide, methane. So all of this to understand how exoplanets work. Look at this. I think that this is absolutely beautiful. This is Kepler 218b. This spectrum is absolutely fantastic. Again, you have wavelength here, and these detections are just, including this interesting detection of dimethyl sulfide here. It's tentative, but for people like myself who don't work in this field, and we're just saying, how do you explain to people dimethyl sulfide? Well, if you Google, you basically get is the smell of the ocean, because it's the sort of interaction of bacteria with water. So take it as, it's a little nugget of possibly science fiction, and the detection is tentative. But again, this is raising the discussion of exoplanet atmosphere completely to a different level. One final word about evolution of galaxies with time, because we're interested to see the very end. So again, this is a little drawing that has been put together based on Hubble observation. Remember, Hubble got us to a certain point. And what did we observe with Hubble? We know the galaxies, how they look today, like our Milky Way would look like this. If you look back in time, with Hubble we could see that they were more and more disorganized, more and more irregular, redder and redder. This is pretty much, sorry, I wanted to show this. This is pretty much the picture of the most distant galaxies taken with Hubble. And so astronomers jumped on JWST and started looking what they could see. And this is what they can see. It looks like there are more galaxies than we would expect. So first result, the number density is higher than was expected. It looks like they are more organized earlier than we thought. So astronomers started scratching their head, and we have experts in the room like Mark who can correct what I'm saying. But this has been an interesting conundrum. How did galaxies really form? How they got organized? How did they went from the little tiny blob to what we see today? And what happened in the universe in the first billion years? How we went from nothing, from the beginning to today. And stay tuned, because at ISSI Bern in March 2024, we will have a big cosmology event that will try to answer exactly that question. We're putting together all the experts, all the people with cosmology program accepted on JWST, and they are coming here in this very room, to argue until we will not provide food or drinks, until they come up with an explanation. I just wanted to show you very quickly, because I know it's late and I've kept you here for a long time, but I wanted to show you some of so I don't work on Webb anymore, but I do science with Webb. And talking about stellar cluster, this is, if you come to my office, you see this replicated in 3,000 different pictures. This is NGC 602, small Magellanic Cloud. What's interesting of this particular object? A cluster was formed out of nothing. The density in this region is incredibly low, but still there is a cluster, and there is still fuel to produce stars. And what you see here, this is the central cluster. These are all stars, very hot, very powerful winds. They have already cleared somehow the central cavity, so they've swept the material out. There are ridges here where we see tiny little stars forming, so we do believe that star formation started at the center, moved outwards, and is now triggered along the ridges. So this we thought, well, first the question is why this formed in an area where the density is so low. It's not in the middle of the cloud we showed you before. It's because there are two big clouds of neutral hydrogen that collided. And exactly in the area where they collided, we can see this cluster formed. We're talking 1 to 2 million years. This is really, really baby talk. And what we're doing is we are looking at it with all different means. So photometry has already been done with Hubble. You see here the central cluster all the way to the ridges that I showed you. So photometry with Hubble, and then you do spectroscopy to try to understand the motion, because we really want to get a 3D view of these objects. From ISO, and then in ultraviolet spectroscopy to understand exactly what we're seeing in the central cluster, and then finally Webb to investigate what we call the young stellar objects, the objects that are less than 1 million years, 500,000 years. There are different classes. We know they are there, but from previous observations, so I shout out here to Peter Zeidler, Elena Sabbi, my former student, my former postdocs, and now, valued collaborators. We are putting this together right now, and this is what we knew before. This was Spitzer. Image of this object taken with Spitzer. You can't see anything, right? The resolution is so. We could see that there were bright sources. Those very, very young objects we can see in this image, but we cannot resolve it. We don't know if they're single, they're double. We can't say much. And so this is where. So, for example, that is an example. So what do? We just got time with James Webb, and it was observed. And this is what we see. And you see here an image that is not. This is not a pretty image. This is the image that astronomers work with to sort of do the measurements. So we do things that we can really look at all the young stellar objects and characterize them. Anyway, and then just for the aficionados, what do astronomers do with these numbers? They put them in color magnitude diagrams that look like this, where there is a specific location where all stars fall. The main sequence where our sun is. The stars that are, left the main sequence appear like the Wolf-Rayet I show you, but we are interested in the pre-main sequence stars, the stars that haven't made it to be a full stars. And Hubble could get to this level of magnitude, a little noisy. Look with Webb what we're doing. You just go down by 2 magnitude with an exposure that is a fraction of the time. So anyway. So this is where they are, because we're interested to see exactly where they fall. Anyway, if you want to learn more, check these 2 websites, isaweb.org and of course web.nasa.gov. And thank you, and I will just leave the credits because clearly this presentation could not be done without the 1,000 people who worked on this project. So, thank you.
Very much, Antonella. This was really great. I mean, from the technological to the beauty to the science, everything is just really wonderful. Questions, please. I can ask one if no one else starts. On this Christmas day,
Yes.
were you also watching? I almost died, I have to tell you, because I was so nervous.
So, on that Christmas day, we were all gathered in the main room at Space Telescope, and I have to say that I don't speak French, but I have to say the best word that I heard in the French language was nominal. We kept hearing nominal, and every time the word was uttered, people were just, the smile was getting bigger. So I had actually, it's interesting because I had an option to go down to Kourou to see the launch, and I declined because I wanted to be with the people. I wanted to be there, with the people who had spent so much time on this mission. And then we knew that the launch was just the beginning. You launch, is great. We understood immediately that things were going well. As a matter of fact, the camera I didn't show you, but the camera, was watching James Webb moving away. And one of the things we saw at a certain point, we saw the antenna deploying, and it was an automatic command, and everybody was sort of expecting that it would show up, but it kind of showed up before, and this is before people expected, and this is because the orbit insertion had been so perfect that condition for the automatic deployment of the antenna had basically appeared well before people had originally thought. At that point, people couldn't believe it. But then they knew that the hard work would start, because all that, the deployment, that is what kept people awake at night for a month. Because, just a technical detail, how do you deploy those things? You have non-explosive actuators. Basically, you can't explode something and open it up, right? Because you could contaminate, you would create all sorts of problems. So these non-explosive actuators were like spring magnets. So the spring would just boom, and the sunshield would open, and the boom would be open. And they had, as I showed you, many hundreds of those. On the ground, they always had failures. Always. Every test, every deployment, they always had failures. And the system was redundant, so they had more, than they needed, but not one failure in flight. So.
Yeah, this was also when the number of things that had to work. With chaos, which we built in Bern, we had one thing that to open. This was the coverage of the telescope, and you had, I don't know, hundreds.
Yes, I can tell you that the engineers and the people who had worked, they were there. They, saying not waiting for a month, everything closed, and then you don't see, right? It's not that you have a camera; you can't see. People were really worried that if something was wrong, you have basically to rely on the telemetry. So that's not.
Questions, please. Yes.
What's the meaning of, you said the telescope is on L2?
Yes.
I didn't understand.
So is the Lagrangian point is 1.5 million miles away from Earth. Why is there? Because it's an area where it's stable. Can stay. You put it there and it stays there, rotating in that orbit that I showed you. It's relatively far away from the sun, so the low temperature can be reached with scheduling the sunshield position. So it has a lot of advantages, and especially, Hubble is in a low Earth orbit. so 350,000 miles, it's now full of debris. You are always, I remember for many years you have to move the telescope so that they don't have stuff that is in the path. And you have the Earth in the middle, so your observing time is limited by the fact that you're so close to the Earth. With James Webb, you can observe. You're limited by other factors, but certainly not by the Earth.
Talking about observational limitations, I was looking at the spacecraft configuration, and I was wondering how because you also want to observe bodies within our solar system, how you can actually make observations in the ecliptic plane?
I think you can pretty much, it's basically scheduling. It's a scheduling issue. So they do that throughout the year with, we have a long-term plan that is uploaded, and then there are, commands that are sent over a week time. And I think they can observe quite a lot, because you cannot observe against the sun, clearly, right? That's
so maybe to make the question more specific, can the mirror be reoriented with respect to the okay, all right.
It's fixed, absolutely.
And it's pointing sort of, the observation axis is parallel to the sunshield, so it's.
So the mirror is looking, it's perpendicular. The tower is perpendicular to the sunshield. The sunshield has to be always facing the sun. So you can always look in the opposite direction, but you rotate, you move, right? So you can look other areas. You rotate around the.
Yes.
Yeah.
So worst case, it means you have to wait for half a year.
Exactly.
When we received these first pictures with all the galaxies from Hubble, I think I remember it took over Christmas to New Year's period to take that picture. So let's say something like 10 days. So how much time do you need now for taking one of these pictures with all the galaxies?
Nothing. that's what it is. Nothing. A few minutes.
Okay.
Yeah. It turns out, I don't know how many people here the deadline was last week, but the limiting factor is actually the setup between one observation and the other, the slew and everything. So it has a lot more overheads. The exposure time itself.
So then the next question is, do you plan to do also a 10 days period picture?
That's a very good question. That's a very good question. I think that they are already thinking about exactly this kind of thing. I think the next large program that will happen will probably be in exoplanet science. They're working very hard about investing a huge amount of time to bring those more and more accurate work on exoplanets. So I think, but we will see. The system is totally peer reviewed. So people propose. I actually learned that we have almost 2,000 proposals this time around. So the oversubscription is approximately 10 to 1. That means every 10 proposals, only one is accepted. It's a peer review system, so astronomers decide. It's double blind, so the proposer do not know who the reviewer is. The reviewer do not know who the proposing astronomer is. And I think they will meet. I can't remember when is the meeting, but in a few months we will know the results, and then we will see if there has been anything that challenging or creative or ambitious.
Yeah, thanks for the great presentation. A lot of colorful pictures. Thank you so much. My question is that, can you study acceleration of the galaxies so that we can understand about the dark matter?
Yeah, that's one. Yes, that's one of the intents, is to look at the motion of galaxies. Absolutely. Yes.
Have they done any studies on that to predict anything about it?
Well, I think that let's say that I think for that we need the near spec pipeline to work really well, and we're not kind of there yet, but it's getting there. There are all sorts of studies, but I think at this point people are in data collection mode.
Thank you.
One way to see back in time is to look for the redshift in the object. Now with James, you can see even more fainter redshift object. How big is the new catalog with extreme redshift objects? Is it a few subtle objects, or how big is the catalog now to work with?
I think we are still there is the occasional one object, a redshift, whatever, 11, 12. This is still one at a time. But there are surveys that are happening already where people are, will generate a much larger. But the quality is so great that we have situations where and I should also say, at the beginning of after the deployment, the 200 hours were devoted to what we called early release science. Early release science were programs that were supposed to sample every field of astrophysics. So exoplanet, planets, blah, 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 everything. And the idea of those was they're proposed, data is taken, and then they're put in the archive immediately public for everybody to take and to use. And some of those programs already generate, people were just downloading from the archive, just extracting a spectrum by hand and then, measuring the redshift like this. Some of the results were off. But yes, there was a lot of that happening in the first, because people were so eager to see what this telescope can do. So.
Excuse me, if I do understand from this question from him, so that James Webb Telescope cannot look at Earth to understand the atmosphere of the Earth, so we can then understand about the exoplanet's atmosphere.
Well, we with Earth, we know quite a lot about Earth.
Yeah, but from the Webb, so that we can compare and contrast with other exoplanets.
So I think that we don't need Webb for that. I think there is a lot of work in Earth observation. Basically, it's probably the best planet we know in terms of data. And so that is going to be compared to what we see in the exoplanets, indeed. But we don't need Webb to look down. We have plenty of other satellites and things that have done that over the years. And our Earth is pretty much dissected pretty well at all levels. Yes?
I have another question. I heard some talk about, and I don't know how reliable or serious it was, about the fact that the micrometeorite environment at L2 is maybe more harsh than was anticipated, and that there have been reported damages. Is there any comments on that?
Yes, sure. So yeah, we had a micrometeorite hit in the first few months. And but I think that statistically it was expected. It kind of, but like all statistics explain, you might have a detection immediately and then nothing for a long time. So the model, there is a model that is actually working pretty well, I hear, and it's exactly what was expected. It's just that one event happened at the beginning and triggered all sorts of panic attacks in the media. Oh my God, the telescope is doomed. Now if we calculate that there will be one such micrometeorite. And it didn't even, they analyzed the impact. It was a strong impact that didn't make any difference. Plus there is so much redundancy. It contributed to a little bit of a loss of signal because that you have a dark area that is not collecting light, but that's the reason why you have also beryllium. I mean, it's a pretty robust system. So I would say that I hear that the model is pretty good, the predictions are pretty good, but like in all statistical prediction, you might be hit sooner than you thought. So people are not worried about micrometeorite. I don't know what.
You showed us the star forming Magellanic clouds,
Yes.
MGC 3, 4, 6. And you mentioned these three clusters.
In the center.
Yeah. I was wondering, so the astronomers speak about the IMF, so the
Yes.
initial mass function,
Yes.
the balance between massive stars and
Yep.
young stars. Is it much different between
No.
these different?
No, it's totally what goes by. So one of the big, so this is a very interesting question because astronomers have always wondered if the distribution of masses in any region is the same. As a matter of fact, it's called mass function, and the question is it universal? So wherever I look, is it the same? And so I can count tons of proposals that had the title, is the mass function universal? Or does it depend on local conditions, like metallicity? You know, this region might have a different metal content than others. And so is that an effect? Is that an impact? The answer, unfortunately, is very boring. No. It's the same. It's exactly the same. So at least we haven't found yet the condition that make any difference. But so far, people are still, but no, it's wherever you look, it's the same.
Antonella, do you want to tell us something about the colors?
Oh, the colors. Yes. Yeah, I think because this is a question they usually get all the time. How are the colors decided? So for Hubble, let me go, and I think I need one of the, because this, if we look back at the spectrum, it will be absolutely clear. This one. Okay, so the colors. If you look at Hubble, right, you have, this is the range from the ultraviolet to the red. Of course, it's pretty much visible, plus really blue, you know, ultraviolet, violet, and then going red, red. These colors make sense. So when you see an Hubble image, and you see blue and reds and whites, they have a pretty good correspondence to the wavelength where that, so a telescope is a monochromatic, you know, image taker. You take images with a filter at a certain wavelength. The image comes down in black and white. How do you provide the colors? Well, if I have an image at 65, 56, you know, H alpha, I know that black and white is probably red and black. And so I can say, when I take an image of any object, and I take an image in the blue, in the white, in the red, then I put them together, and I get pretty much a true color. So if I could see with my eyes at those images, if I could, you know, just have a telescope that shows me that level of detail, it will look pretty faithful to the original, you know, wavelength the colors were emitted. Now, the entire thing changes when you go in the infrared, because now you are operating in this regime. It's all red. And you've seen, so I can say that if I look in the near infrared, it's probably a little lighter red than the mid infrared, which is a dark red, but it's all red. I don't have any more a spectrum of colors to use. And so, as you see, some of the images I show you were only red because they were faithful to the wavelength they were taken in. And so there was, at the beginning, that was the philosophy. So our image processor thought long and hard whether that was the way to go. And then people didn't like it. People thought that the images were flat and they didn't have dynamic range. So somebody else came out with another idea, and they said, well, suppose that I'm now looking in this regime, right? And I say that this part here, which is my near infrared, is bluer than this part here, that is really red. And I kind of go the same little game, blue, white, yellow, orange, red, but I shift it. That's why you see the images that I showed you, some of the images that I showed you, which are blues and reds, and they had nothing to do with the original wavelength they were taken. So that is not a true representation anymore. But when you see an image that is shades of hues of red, it probably is correct. So this is just so the images that you see with Hubble are pretty true to nature. With but the Webb is tougher.
Thank you very much for the explanation.
Thank you.
Except if there is another very urgent question, we can also ask questions later during the apéro. I would like to thank you very, very much. Again, Antonella, thank you for the great talk.